Hi, everybody. All right, we've made it. This is the last day of us testing with series, and this wraps up our Unit 1 series. So you might want to make sure you've got your flow chart handy. We're going to refer to, one or two things on the flow chart here. We'll be talking about the alternating series test, which is going to be one of our go-to tests a lot of times. You can see that's why it's up towards the very top of the sheet next to p-series and geometric series. We'll also see how with alternating series we can easily find what we call the remainder or the error bound, which can be a lot easier than Lagrange. And we're also going to look at testing endpoints of intervals of convergence. When we are dealing with a geometric series, we do not need to test the endpoints, but when I'm doing a ratio test, we really should be checking the endpoints. And now that we have all of our tests under our belt, it should be a pretty easy process to do. So as always, make sure that you're copying down examples with me. I'm going to have you try a problem or two to make sure that you pause and give it a shot. And make sure that you're ready to ask questions. And most of all, make sure that you're practicing some of the problems that I'm asking you to play with. All right, so let's get going. So this alternating series, we've been throwing that word around a lot of times here recently as we talk about series. And yeah, the signs alternate, plus, minus, plus, minus, plus, minus. So the good news is that it's really easy to test an alternating series if it converges. So if we take the absolute values of the terms and that approaches 0, and there's one more condition that I don't have typed here, is that the a sub nth term must be less than the a sub n plus, the a sub n plus 1 term has to be less than the a sub nth term. Each term successively has to get smaller and smaller and approach 0. If that happens, then your alternating series converges. So for example, here is a series that we go to quite often. So I got 1 minus a half plus a third minus a fourth. So it alternates, and I can see that from the -1 to the -1 to the n plus 1 term. So they're really easy to spot when we're given their general terms. So does each term get smaller and smaller and smaller, or their absolute values? Yes, they do. And do the terms head towards 0? Yes, they do. So therefore, this series converges, and it converges by the alternating series test. However, it's convergent, but not absolutely convergent. If I took the absolute value of this series and looked at that series, well, that's a p-series with a p-value of 1, and that diverges. So, and that's the harmonic series. So the harmonic series diverges, but because it is a p-series of 1, but the alternating harmonic converges because it's an alternating series whose conditions are met. So in this case, converges itself, but the absolute value of this series does not converge, so we say it's conditionally convergent. So that's how we would describe this particular series. All right, please note that this does not test for divergence. And I'm going to go back real quick here to go back to my alternating series. You can see, even in my flow chart, there is nothing about it that tells me that it diverges, okay? So if it's alternating and doesn't follow the general rules of each term getting smaller and all the terms heading towards 0, we can't use the alternating series test, and it doesn't mean that it diverges. So let's look at this one. Oh, I guess this is the one that we just looked at. Yep. So conditions that have to be met. Is each term getting smaller and smaller? Yes, it's monotonic. It's always decreasing. And does the nth term approach 0? And it does. Get smaller and smaller and smaller as n approaches infinity. And if I were to actually graph these points, these for each n value, you can see it's alternating, going back and forth, pinging back and forth between plus, minus, positive, negative, heading towards 0. So therefore, this will converge by the alternating series test. So what about this one? Maybe pause and think about this one and then turn me back on. Well, it's alternating for sure. That's this term right here. So what happens as the terms that they head towards infinity? What is the nth term approach? Well, n plus 1 over n itself, that's going to approach 1. So the terms will the terms get smaller and smaller? Probably here, but the terms aren't going to head towards 0. They need to head towards 0. So this diverges. And this diverges, be careful, not because the alternating series test failed, it diverged because of the nth term test. The nth term does not go to 0. So a lot of times the alternating series test and the nth term test kind of go hand in hand. So again, this didn't diverge because of alternating series test, not conditions not being met, diverged because the nth term didn't go to 0. Okay, and that's what we're saying here. Doesn't mean it diverges just because it fails. Nope. So we proved it by the nth term test. So hopefully you see how that kind of comparison happens. All right, so since each term of convergent alternating series moves the partial sum a little bit closer to the limit. So partial sums, remember, are if I take the sum of the first 2 terms, and then the sum of the first 3 terms, and then the sum of the first 4 terms, and the sum of the first 5 terms. We look at those sums. Well, each time that I add an additional term, yeah, the sum is getting larger, but it's not getting larger by much. So when we start talking about error and error bound for alternating series, that gets really easy, because for a converging alternating series, the truncation error, meaning the terms that I chopped off, all of the terms that I didn't include, if I'm doing a third partial sum, the 4th term all the way to infinity, that's my truncation. The truncation error is less than the first missing term, and it has the same sign. So how does this work? It's going to work a lot easier than Lagrange. So we like dealing with this. So what I want to do is this particular series, so make sure in a second you jot this down, approximate the sum of the following convergent alternating series by evaluating the first 3 partial sums. I'm going to look at the first 3 partial sums so you can get an idea of what partial sums are. By the way, this was converging because it is an alternating series. The terms are going to get successively less and less and less, and then they are going to head towards 0. And then we're going to estimate the error or the error bound with this alternating series. So let's take a look. So by putting in n equals 1, I'm going to get 1 over 1. And that's positive, so that's 1. My second sum is going to be n equals 1 and n equals 2. And that's going to give me negative a half. And then so I get 0.5. That's my second partial sum. Then I go to n equals 3. I add the n equals 3 term. That's 1 over 3 factorial. And that's going to be positive. So that's going to be to the 4th power as an even power. If I add those up, I get 0.666667. So I can see my sums are getting smaller and smaller and smaller as I add. Or I'm sorry, they're getting larger, but not by a decreasing amount each time, sorry. So therefore, the error, if I just do a third partial sum, the error between that and the actual sum itself, the most that the error could possibly be is the next term in the series. And the next term in the series would be 1 over 4 factorial, or 1/24. So the amount that I chopped off is going to be less than 1/24 if I do a third partial sum. So this one's really easy. Lagrange deals with typically dealing with power series. Here we're going to be dealing with numeric series of an alternating series. We'll make sure that we look at some more examples of this. All right, so the last thing is we're going to take a look at is with a power series. So my polynomial functions, I know the interval of convergence. If it was a geometric series, r is between -1 and 1, not inclusive of the 1 and -1. But if I do a ratio test and perform the ratio test and find the interval of convergence and make sure that that absolute value expression is less than 1, well, when I solve, I really should be testing the endpoints for convergence. So it is possible that I have a center of convergence and then some radius in each direction, and both of the endpoints come out to be divergent. That's what typically happens that's what happens in a geometric series. Those endpoints are not included. But I might have a situation where one side is converging and the other endpoint is diverging, or vice versa. One side's diverging and the other side is converging, or both of them could converge. And again, so this happens with our ratio test. This is a really typical question on the series free response questions because you have to perform the ratio test first, which involves that algebraic manipulation of the limit. And then using a couple series tests, 2 in fact, 1 for each endpoint, to see what you get. Okay, so I want to find the interval of convergence of this particular power series. Now, again, if we figure out what the interval of convergence is, what we don't know is what this is converging to. We don't know the function that this power series is representing, but that's okay. We're just interested in the interval of convergence. So what I'd like you to do is to pause me right now and go ahead and just do the first step of actually performing the ratio test on this series so you can figure out the interval itself. And then I'll talk in a minute about testing the endpoints. So go ahead and perform the ratio test on this series. All right, so here's my work for the ratio test. Here's my a sub nth plus 1 term times the reciprocal of the a sub nth term. And some of you are skipping this step at this point, but I'm separating out the x to the nth and x to the first so I can cancel those out. Remember, my limit is in terms of n, so that x term I can really factor out. Don't forget the absolute value. And then the limit that's left over, well, hopefully you can see either through a L'Hopital or an end behavior model, it just comes out to be 1. So therefore, I have an interval of convergence between -1 and 1. But I have to test the endpoints. This did not come from a geometric series. So what I'm going to do is I'm going to let x equals -1 and put that into my series up here and determine if that particular series converges or diverges. Then I'm going to put 1 in to this series and look at that a sub nth expression and see if that converges or diverges. Why don't you go ahead and pause me, put -1 in and then put 1 in and take a look at those two separate series and see if you can determine if they converge or diverge and by what reason. Now I'll give you a hint. Typically, these reasons are one of those top 3 reasons on my geometric or my series flowchart. Just look out for geometric series, p-series, and alternating series. All right, so here's me testing those endpoints. -1 goes in, and I get this expression, and I can see it's alternating. The terms are getting smaller. The absolute value of those terms are getting smaller and smaller, and they're heading towards 0. So therefore, this converges by the alternating series test. This endpoint value will converge. And on top of it, this is the alternating harmonic that I showed you before. When x equals 1 and you put that in there, well, then I don't get an alternating series this time. I just get this series of 1 plus a half plus a third plus a fourth. But frankly, I notice this, it's really 1 over n. That's a p-series. So it diverges by the p-series test because I have a p-value that's equal to 1. Remember, less than or equal to 1 diverges for the p-series. And that's my harmonic series. So therefore, my interval of convergence is -1 inclusive to 1 not inclusive. So again, I don't know what that original series itself is converging to, but I know it's only converging between -1 and 1, inclusive and not inclusive. So again, typically these series little tests will be either through the geometric series, p-series, or through an alternating series. All right, I got one more for you to try. Why don't you pause me again, try this all the way through. Perform your ratio test, get your interval of convergence, and then test the two endpoints to see if the endpoints themselves converge or diverge. So go ahead and pause, try this last example. All right, performing the ratio test on this, this should feel kind of similar to the last one, obviously the same setup here. And I go through and cancel out x sub n's, can factor out another absolute value of x, and I get this quadratic over another quadratic, which I hope you see pretty easily through 2 L'Hopitals or through an end behavior model. It's going to come out to be 1. So once again, I'm in between -1 and 1. So now I have to test the endpoints. And when I put -1 in, I get another alternating series. The absolute value of those terms are getting smaller and smaller, and they're heading towards 0, so the both conditions are met. So therefore, it converges by the alternating series test. Nice. And then when I put 1 in, I get 1 over n squared, and I'm writing the terms out. You don't necessarily need to write the terms out. You might just be able to tell just from this general term. And sure enough, there's my p series, 1 over n squared. And that's a converging series because p is greater than 1 because I have a value of 2. So therefore, the interval of convergence is -1 to 1 inclusive. And again, you can use either inequality notation, interval notation. It doesn't matter. And that's it, guys. That concludes what we're going to be doing for series. You have to make sure that you're practicing these, making sure the more you work with these series tests, the more that you're going to probably become ingrained. And again, you'll definitely have some series tests that are going to be go-tos versus others. So make sure you practice. All right.